Welcome to the seminar. So we're very happy today to have Martina Neuman from the University of Vienna. So she got her PhD from UC Berkeley, and her research interests are in harmonic analysis, low-rank geometry, mathematics of machine learning, and she works on things like optimal transport and spectral graph convergence, compressed sensing. Currently at the University of Vienna, she's working on a project to do with singular structures in deep learning, and she's active in the applied harmonic analysis group there. So she's going to talk to us today about transferability of graph neural networks via Graphon and sampling theories. So,
okay, well, thank you. Thank you for having me. Yeah, so the title of the talk today is transferability of graph neural network GNN via Graphon and sampling theories. And this is joint work with Jason from Concordia. So this is a typical work where we use basically mathematical tools in order to explain achievability of a certain property in neural networks. But before I could explain to you explicitly what we do, I would have to explain to you certain core concepts first. Okay? And so we're going to start with the first core concept. As you could see, that's about Graphon. So Graphon is basically just is giving you a notion of graph limits. So imagine that you have a evolving network, and every time the network updates itself, it gives you a new graph. Let's say that you have more nodes and you have more edges, okay? And you observe that you wonder if there's any kind of a convergence sense at all. Okay, is there any kind of saturation state? Okay, related to that kind of question is the question of like how to compare two graphs of different sizes. Okay, so for instance, I prepare for you here like two very simple examples. Let's just say that you have a cycle G, and you decided to modify G a little bit. So you give G an extra edge, let's say that the G plus, okay? And you want to compare between G and G plus, and it's not entirely hard, right? You could take a look at the adjacency matrix of G, called A, and you could take a look at the adjacency matrix of G plus, called A plus, okay? And then you could take a look at the Euclidean distance between A and A plus, and then you could compare G and G plus that way. After all, the adjacency matrix of a graph is going to store all of the connection information of the graph itself. So that's the most essential information about graphs. And then you could raise your hand and say, okay, what about like no relabeling issue? Well, then before you take the Euclidean distance, you might have to mod out all of the orthogonal action before it makes sense. Okay, but it's not entirely hopeless to compare between G and G plus. But what happened if you decided to modify G is a little bit different, okay? So if you given an extra edge and now you also give an extra node as well, then this kind of like method breaks down, because now the adjacency matrix you look at, one of them is going to be 5 by 5 and one of them is going to be 6 by 6, okay? And then you cannot compare in this way anymore. But then if you take a look at these two examples here, you could see, okay, there's something strange here, because I could see that both G plus and G plus plus, they are simple modification of cycles. But yet I could like have a way to compare G plus with G, but not G plus plus and G. Okay. You could see that these two problems are actually related to each other, because if you have a sequence of graphs, and then you could say the sequence of graphs converging somewhere, you could take the two guys in the sequence and you could try to compare the distance between the two, like let's say in the sense of Cauchiness. Okay. All right. So that is kind of motivation of like why that we cared about this kind of like problems. All right, so I'm gonna, in the first two slides, I'm gonna give you simple examples in order to invoke intuition. And then after that, I'm gonna give you scientific definition, okay? All right, so let's say that now you have a stochastic block model. So stochastic block model of two end nodes. So here you have one end representing one political party, the other end nodes representing another political party. And you say that, okay, so this is a random graph, okay? And you say that the two guys in the same political party have a chance to connect to each other with the probability 0.8, okay? So the edge that form between the two is 0.8. Okay, the two guys across the aisle talk to each other with 0.2 chance. Okay, so the edge is formed between the two. Okay, it's going to be 0.2. Okay, and so you could say that, okay, fine. Let's just say that you have that kind of like model and you decided to update the number n. Okay, so instead of you take a look at like 2n, now you're going to take a look at 2n plus 2. You take a look at 2n plus 2 2n plus 4, and so on and so forth. And then I could ask you point blank, what is the difference between the model that has like 2n plus 2 and 2n nodes? If you tell me the difference is the number of nodes, it's going to be way too trivial, right? Because the dynamics remains the same. Okay. Okay, so here is kind of picture for me to try to invoke intuition here, but when I run that with a domestic audience, I kind of like, mess them up a little bit. So here I just try to draw for you the expectation of the adjacency matrix, because again, it's a random graph, right? So when you draw the expectation of adjacency matrix, you could see that it has 4 blocks, 0.8 over here, 0.2, 0.2, and 0.8. And even if you increase the size, the dynamics remains the same. So there's some kind of like sense of limit in this very simple example, okay? And here is just a little bit about the motivation of why we care about such a problem. So if you have a recommended systems that has the end users, so the number of users could like come and go, and you don't want to retrain the whole neural network all over again just because a few guys decide to get out. Okay, all right. Okay, so now we're gonna go to the definition of a convergent sequence of graph. Okay. So I say that Graphon is a notion of graph limits, right? So I'm gonna give you a definition of convergent graph first, and then I'm gonna tell you what the graph limits is. So there's 2 things, okay? All right, let's just talk about convergent graph sequence first, okay? By the way, Graphon theory is very young. It's about like 10 to 15-year-old. But Graphon neural network is even young. It's about 5-year-old, okay? All right, so if you have a sequence of graph, GN, and let's just say that n here denoting the number of nodes. By the way, if I happen to be fast, you can slow me down, ask to slow me down, okay? And here I have not specified what kind of graphs that I'm gonna concern about, right? Okay, so the Graphon theory that I'm discussing here is applicable to weighted graph, unweighted graph, and also for random graphs. So stochastic block model is a random graph, I just show you, okay? But like to set up the theory, let me just talk about unweighted graph first, deterministic unweighted graphs. And all of the graphs that we concern here is gonna be simple and undirected, okay? All right, so let's just say that I have a sequence of graph GN, and is denoting the number of nodes. And right now, for simplicity, just gonna think of that as an unweighted sequence of graphs. Okay, and to determine whether this sequence is gonna converging somewhere or not, there's actually 2 ways for you to determine that. So one way is through the cut metric, and the other way is through the homomorphism density. So cut metric, I'm not gonna talk about that here. So cut metric is actually related to the notion of graph cuts, and it's actually quite, it doesn't really give me much intuition. So I decided to talk about homomorphism density. Okay, so homomorphism density is just a way for you to capture subconfigurations within a graph. Okay, let's just take a look at one graph LGN, and let's just take a look at the simple graph F of K node. Okay, we're gonna call F a motif, and then we're gonna consider this number here, T of FGN. Okay, so this number here is basically just gonna be a the ratio of the total number of graph homomorphism that map F into GN. And divided by the n to the k. So n to the k is going to be the total number of maps that map k point into n points. That's it. It's extremely crude, the denominator. Okay. The numerator, again, is going to be the total number of graph homomorphism that map F into GN. Okay. Graph homomorphism preserving edge, but not non-edge. So in other words, you could map multiple nodes into one point. Okay, so there's not a lot of bijection going on with the graph homomorphism. Okay, and then you say that, okay, so you say that the sequence of GNs is going to be a converging graph sequence if the number TFGN here, so this is the sequence of numbers, right? So you have a sense of like convergence of a sequence of real numbers. So for every F, you're going to test it out, and you're going to have sequence of numbers here. And this sequence here converging for every F, of course, on board, okay? Then we say that GN is a converging graph sequence. Okay, does that make sense here? All right. You could see what I kind of like this kind of definition because I'm an analyst. Okay. So in analysis, if you want to test out a sequence of function GN converging pointwise or not, you're going to test it out with a test function now. Okay. Notice so far that this is only give you the conclusion whether GN converging or not, but it doesn't give you a sense of Cauchiness. For that, you would have to take a look at the cut metric, and I'm not going to discuss this here. Okay. All right, so far so good. All right, so here we're gonna have, we have to discuss a few technicalities. So remember the whole thing about graph node relabeling, that's a big issue. Because certainly if you decided to all of a sudden relabel all of the nodes, the number of homomorphisms should stay the same. So therefore it creates some kind of non-uniqueness in the limit, but that's okay. Because you could like mod out an equivalent class at the end. Okay, so that's gonna be taken care later. And here is just a little bit about a history. In the beginning, what they consider is a total number of graph isomorphisms. So if there's a, they consider bijection as well. The total number of graph isomorphism divided by all of the possibility of like mapping K point into N point. But the thing is that the number of graph isomorphism is actually very hard to calculate. So they decided to relax it to the number of injective graph homomorphism. But it's still hard, so they decided to go all the way down to graph homomorphism. And of course, along the way, you would have to have some kind of justification. Okay? But long story short, the reason why they decided to go down to all the way to graph homomorphism, because there is an alternative formulation to 1, which is 2 right over here. Now, neither 1 or 2 appeared in my work, but like for the sake of completion and also the setup of 2 is going to be quite relevant to the story that I'm going to tell later. So I'm going to decide to explain this formulation anyway. Okay. So far so good. Okay.
So in this last one here, W is the weight matrix for the graph.
Yeah, I'm about to explain as well. Yeah. So just like FYI, this actually doesn't really appear in my work. Okay. So yeah, on the left-hand side, you have GN. On the right-hand side, you have WGN. So certainly these two related to each other, okay? So W here stands for weight, okay? So as you kind of like suspect that, WGN here is gonna be a basically extension of the adjacency matrix of GN to the continuum. Okay. WGN here, you notice it's gonna be a function of 2 variables, and K here is corresponding to the node of F, okay? So how does it work? All right, it's actually very simple, the whole idea of throwing every discrete graph into the continuum, okay? Suppose right now that you have a graph G, and let's just say you have n nodes, okay? And then you're gonna throw all the nodes to the continuum, which in this case is gonna be the interval from 0 to 1. The way that you're gonna do that is that you're gonna take a node VI and map it to the point I minus 1 divided by n. So in this case, the node V1 is mapped to the point 0. It's just that, okay? But of course, you would have to know your node labeling already, okay? But this is not really like it's not really like keeping track of graph, right? Here it's just like you throwing nodes onto the interval from 0 to 1. Graphs is about what? Connections. So therefore, you would have to keep track of the connection. And the way that you do that is that you can make 2 copies of 0 to 1 with the partition point from the node. Oh, by the way, I totally forgot like how to like throw it in. So you could see that the partition here is 1 over n. N is a number of nodes of G. Okay. All right. So now you make 2 copies of the partitioned interval from 0 to 1, and then you make a square out of that. So this is a total of 0 to 1 square, the unit square. And then you're gonna make the subsquare out of the partitions, okay? And then you're gonna take a look at the 1 subsquare, and suppose that the top left corner, the coordinate is I minus 1 divided by n, j minus 1 divided by n. Then you're gonna assign this subsquare a value. That value is gonna be the adjacency, the value of the value ij of the adjacency matrix A of G. Okay, that's it. Okay, so what do you do next is that now you have a unit square. You're gonna need to raise each subsquare to the value prescribed by the subsquare. So along the diagonal, you could see it's gonna be all 0, right? Because AII is equal to 0. We have simple graphs. So you don't raise anything at all. But anything that has a value 1, you're gonna raise it up to the value 1. Okay, so when you do all of that, you're gonna have what is a graph of a simple graph. That is gonna be your WGN. Are we okay? So this is a stepwise graph. Okay. So first of all,
Where do you see F here?
what F?
So
So far, what I'm describing right over here, you could see the red thing right over here, right? Is only how to extend A to a function WG. So I have not touched F yet. Okay, I just wanted to tell you that when you get the WG, this is a function that associated with the adjacency matrix A of G is basically, it's just a stepwise function. Okay, and the way that you raise it up is just based on the value that you get from the subsquares. It's that simple. Okay, so now we have an idea of what WG looks like, then we can plug it in. That's what I'm trying to say. So for instance, here I prepare for you a very simple example. If F is a triangle, well, K is equal to 3, okay? And then you're gonna have like WG of WGN in this case of X1, X2, so one edge, X2, X3, one edge, and X3, X1, the other edge. Okay, so this is just an example of how to plug it in, and that's why that formulation 2 is preferred, and that's why the graph homomorphism is preferred. Okay. But the idea out of here, I want you to get is how to extend adjacency matrix into a function of 2 variables, WG, because this is important. Okay.
Can I ask, like, this is what you, in the previous slide, you said, of course, it depends on how you relabel the nodes, right?
Yeah.
And so here, this, this is not there's no unique way to.
Yeah, I'm about to get there.
Graph.
Yeah. Okay, you're gonna spot that. Okay, all right. So now that we have a way to extend A to a function WG, here's a theory. So suppose that you already determined that the sequence GN converging to somewhere. Okay, then the theory goes that if you have a sequence convergent graph sequence, there exists a symmetric function W that lives on the unit square 0, 1 square, go to 0, 1. Oh, sorry, I have to like take a step back. Okay, let me just take a step back. So remember the way that I extend A to a function WG, okay? It doesn't matter what kind of value of A takes, right? You could have like A to be 0, 1 or 0, 2, 1. So therefore, this theory extends readily to the case of weighted graph, okay? So this is the reason why I have the limit here to be taking the value from 0 to 1. Okay. Once you have in your hand a convergent graph sequence, there exists a limit that looks like this. So this is the limit right here. It's going to be a function on a unit square, 0 to 1 square. Okay, mapping to 0, 1. So far it's just about deterministic graph. Okay, so the limit here is going to be a function that lives on the unit square 0, 1 square, and it's going to be quite strange at first, but it's not exactly that strange. Okay, first of all, think about it. The limit cannot be another graph because you can only throw nodes in. Okay. Secondly, if you imagine right over here the way that we push G into the interval from 0 to 1, if n is getting larger and larger, then the grid's gonna get closer and closer to the home interval from 0 to 1. So therefore, you could think of the home interval from 0 to 1 as an uncountable graph. Okay, so if WGN is going somewhere and WGN is supposed to store for you what? The graph connection information, then the limiting object would have to store for you the connection information between 2 abstract points X and Y, where XY lives on the interval from 0 to 1. So therefore, in this case, the limit will have to be a function on the unit square 0, 1 square. Okay. Another thing that you should remember that like this is not the first time that you see where that the limiting object is something else different. So if you will remember your, calculus. Okay, one way for us to completely realize that you're gonna throw everything into a limiting space. Okay, so when in that limiting space, every element is a Cauchy sequence of rationals, and that element right now representing a real number as well. So it's not the first time that you see the limiting object to be something quite different. Okay. All right, so Jeff kind of spot me there, but it's going to be in the next slides. The limit, actually, technically speaking, is not going to be a function, but it's going to be an equivalent class of function. Okay. Okay, so the last one is how you're going to extend it to the case of random graphs. It's actually quite easy. So when you have the random graph, GN, then the adjacency matrix AN is going to be random matrix. Then this element right over here is going to be a random element. So when you take the expectation of WGN, it's going to be an extension corresponding to the extension of an adjacency matrix of a deterministic graph. So in that way, you could like refer everything back to the deterministic theory. Okay? So for instance, in this case, in this example right over here, if you take a look at this adjacency, oh, by the way, forgot to say. So in the case where GN is a sequence of random graphs, then you have this kind of limiting here happen with probability 1. Okay, so that's how you stand it out. So in the case when you have the stochastic block model, then the limit is going to be a step graphon, just like the one that I draw before. You have like 4 subsquares, 0.8, 0.2, 0.2, and 0.8. Okay, the convergence is going to be with probability 1. Okay, so far so good. All right, so here we're going to talk about address the non-unitedness in the limit. Okay, so yeah, the all right, let me just draw something. So technically speaking, the limit is not going to be a Graphon function, but it's going to be a family of equivalent family. So equivalent family of rearrangement of a Graphon. So let's just say W psi. Okay. So if you have a Graphon function W, this is going to be considered to be equivalent to its own rearrangement. Oops, sorry. W phi. W phi. Okay. W phi is this defined to be like this. So XY is going to be W of like phi X and then phi Y. And what is phi? Phi is going to be a function that mapping the unit interval to itself such that phi is bijection, phi is measurable, and also measure preserving. So right away, you could think of that as a continuous analog of node relabeling. Okay, so it's not, the limit is not going to be a function, but it's going to be equivalent class of function, but that's okay because you can always work with one representative. Okay, another thing is that, okay, so this is what I say here, Graphon theory for dense graph. Well, technically, this Graphon theory that I'm presenting is going to recognize every sequence of sparse graph to have limit 0. It's not very strong topology. Okay, it's actually kind of expected because, oops, sorry, where am I going? Yep, it is kind of expected because, like in this case, when you have sparse graph, right? Then the ratio of like the edge En divided by n squared is going to go to 0 and n go to infinity. Okay, so therefore this limit right over here at n go to infinity would have to converge into Tf of W, where W is going to be non-negative function. So therefore that W would have to be 0 function. Okay, zero Graphon in this case. But that's okay because like there exists a Graphon theory for sparse graph, but unfortunately I didn't know about it before I started this project. Okay. Okay, so that is one thing, but that is not the only power of Graphon that I'm gonna need. I need something else from the Graphon. So now that you have a notion of graph, a sequence of graphs converging to somewhere, okay, that's Graphon right over there. I want to be able to generate graphs out of this Graphon. If I have that Graphon and I can generate graph out of that Graphon, then I could treat my graphs at a hyperparameter when I design a graph neural network. Okay? And the way to do that is actually quite simple. It's exactly what you expected. Okay. So suppose that I have a Graphon W, and I want to generate out a sequence of GN converging to W. There's 2 ways for me to do that. Let's just say that I want to generate out a sequence, a deterministic sequence, and I also want to be able to generate out a random sequence. It's actually quite simple. Suppose that you already have a bunch of nodes waiting for you, let's just say n nodes, and all you need to do is to take a look at node Vi and Vj. Okay, and you're going to try to see, you're going to take a look at Wi minus 1 divided by n and j minus 1 divided by n. And if this is positive, then the node Vi and Vj is going to be connecting to each other with the edge weight that is equal to this value. Okay, that's all it is. Now, in the case where you want to generate a random graph, suppose the same thing, you have n nodes waiting for you, and you're gonna take a look at, let's say, Vi and Vj. And then you're gonna take a look at the same thing again, the value of Wi minus 1 divided by n and j minus 1 divided by n. If this thing right over here is positive, then Vi and Vj is gonna be connecting to each other with the probability that equal to this number right over here. So it's very simple. Another thing that I want you to know, and again, it's actually quite simple, but it's gonna be related to my work later, is that if you take a look at the adjacency matrix of the random graph, then the expectation of that is certainly is gonna be equal to the adjacency matrix of the deterministic graph, okay, generate out of the same family W, okay? All right, and so, all right, so this is where I'm gonna, okay, so this is where I'm gonna start to set up my problem. Okay, so far that we have a sequence of graphs converging to somewhere, that somewhere is a graphon. Now, the philosophy that we use in graphon neural network direction is that, well, the network that works on this sequence of graphs gonna converging somewhere. That somewhere is, we call it the graphon neural network. So it's gonna be an abstract neural network that works on a graphon. And what I must warn you here is that it's just a philosophy for us to work with. Basically, it's gonna be some intermediate modeling steps, okay? So before I give you a scientific definition of like, what does it mean by sequence of graph converging to somewhere? Here, we don't really have that kind of like definition. It's more like a philosophy point, okay? But let me just go to the next slide. The previous slide is quite fast, okay? The problem setup for us is something like this. Now, suppose that I have a sequence of graphs that converging to a graphon in a way that this sequence of graphs is actually generated out of that W, okay? And I want to be able to, okay, so on each GN here, I do have graph signal Fn, okay, on graph signal Fn here. And I want to be able that on each GN build a graph GNN graph neural network that could learn, not only learn Fn well, but also adapt well to the change in the number of nodes as well. Are we okay here? Okay. And the way that I'm gonna do something like that is that I'm gonna take all the way to the limit. When I go to the limit, I have a graphon, right? And I'm gonna build a neural network that works on that graphon. Okay, that's an abstract neural network. Then I'm gonna discretize that neural network, and the discretization is gonna become my GNN. Okay, so far so good. Okay, and there's a few things that I would have to assume too. Well, so far that I have like GN converging to W, I would have to make some assumption about my Fn, the graph signal on each GN, in order to work with it. Well, I want to say that there is a limit for Fn at the end. The limit of that is going to be a graphon signal. A graphon signal is just a function that lives on the uncountable graph, which is, in this case, just an interval from 0 to 1. And I want something else out of that as well. So I want to have some consistency. And the consistency is that the value of the graph signal Fn at the point Vi is going to be exactly equal to the graphon signal at the point I minus 1 divided by n. Okay, and the way that I'm gonna need to also work with the graph signal that has thrown to the continuum too, because Fn here is still a function that lives on graph, but I need to work with everything on a continuum. So I'm gonna have to like find a way to extend the Fn to the continuum. And the way that I extend Fn to the continuum is actually quite simple. So first of all, I'm just have to identify each node Vi with the point again, I minus 1 divided by n. So it's gonna be a bunch of nodes, bunch of partition point on the interval from 0 to 1 already. And so let's just say here I have like V1 is gonna go to the point 0 right over here. And let's just say that the graph signal value at the V1 is 1, so I have 1 here. And the graph signal at V2 is 3, so I have it here. And here's 2, and that's gonna be -1 here, okay? And all I need to do is just extend it stepwise. And this extension right over here is gonna be the graphon extension Fn bar of Fn onto the continuum. So far it's just a bunch of like very simple extension, but bunch of like terminology. Okay. All right, so I need that consistency in order to work with. Okay, so now I'm gonna discuss a little bit about the WNN and GNN structure. By the way, WNN is just a notation for Graphon neural network. So W is just a Graphon notation. Okay. So far, I kind of like hint for you that the way that I'm gonna do this is like bring everything to the continuum, modeling up in a continuum and discretize it. And that discretization is gonna be my GNN. So I might as well just make everything parallel to each other. Okay, and you could see here that both neural networks that I have is like 2 layers because the tool that I'm about to use allowed me to go to only 2 layers regardless. Okay. By the way, how many of you like familiar with like neural networks? Okay, all right, cool. That's cool. So maybe I could like go fast on this. Okay. All right, so the GNN that I have is, and if I happen to be so fast, then you could like slow me down. Okay, so for the GNN structure, I only need like 2 layers. Okay, so again, for the first layer, I'm gonna have like input in, and I'm gonna apply the fine transformation on that. So I'm gonna apply a weight matrix to it and then shift it if I want to. And I'm gonna do an activation. An activation here, I'm gonna use a ReLU, okay? And I'm gonna do the filter, the graph filtering. And of course, I know that, if you're familiar with graph neural network, you could ask like, why is it I do the filter layer? Well, that's because that's gonna, if I do the filter layer, it's gonna allow me to use sampling theory in, okay? By the way, you're actually quite free in rearrangement all of this operation here. Okay? The last layer, I'm not gonna do filtering, of course, we don't do that. And I'm not gonna do activation as well. Okay, so parallelly for the structure of Graphon neural network, I'm gonna do the same. I'm gonna have the input in, apply to that an affine transformation, and do an activation and then filtering. Okay, now here's the thing: you could see that I draw a small x and small y. That because I work on everything that I work on now is gonna be on the interval from 0. So the 0, 1 here not only is gonna be my uncountable graph, but because the node here is going to be the abstract point on the interval from 0, 1, I might as well just take my input feature to be the location of the abstract node on the interval from 0, 1, which is x itself. Okay, I have to emphasize this point because this is the reason why I have only 2 layers. I kind of bypass the curse of dimension, right? If I bring everything into 1 dimension setting, I don't have the D problem. I don't have D-dimensional problem. Okay. All right, so again, as I say, the Graphon neural network is actually quite young. So right now there is not like a lot of standardization yet, but because I want to make everything parallel to each other. So if you understand that graph filter is like a function in terms of the immediate input feature, and is also implicitly depends on the graph topology, and it's give out an output feature, then I would have to define similarly that Graphon filter take in input feature, and then kind of depend on the Graphon information and give out something. Okay. And I'm gonna give you the next slides, hopefully so, or not there yet. But in the next few slides, I'm gonna give you a very specific construction of Graphon filtering as well as the, here, I guess, okay, we have some information here, and also graph filter as well. Okay, so ignore the 3 in a little bit. I'm gonna talk about it in a second. But yeah, let me just talk about this 2 first. If you take a look at the literature of Graphon neural network, you could see that most of the time you're gonna see this representing a Graphon filter. So this is what they take so far in the literature to be a Graphon filter. You could see that it depending on the Graphon information, and this is just a convolution against the Graphon. Okay. But for our purpose, we're gonna need something like more stronger than that. So we decided to use these operations instead. So K here is gonna be some kind of modification of W, and I'm gonna make K to be a little bit more liberal. So K, the value of K gonna be real value. It doesn't have to be restricted on the interval from 0 to 1. And K doesn't have to be symmetric in terms of X, Y. That's what I need, okay? So to differentiate between the 2, I'm gonna call the first one Graphon operator, and the second one is Graphon filter operator. So this K here is a kernel, filter kernel, okay? Now, because I'm gonna pretend that my GN is like generate out of the W, a graphon W. So I want to make my W as general as possible, but not too general because otherwise I cannot do math on that. So the way that I assume on W is something like this. I do not know where my W is equal to 0. Okay, if you have like W to be positive everywhere, basically you have a sequence of very connected graph, like complete graph that matching to W. But you can, you don't really have that all the time. So I'm going to assume that W that could have 0. However, I assume that there is a good diagonal band on which W is going to be positively bounded below. And not only that, on that diagonal band, I have my W to be sectionally Lipschitz. Now, sectional Lipschitz certainly imply a stronger global Lipschitzness, but I don't need that. I only need this kind of inequality here. Okay, and that would be enough for me to use my math. Okay, lastly, I would have to say something about this limiting graphon signal too, because otherwise, again, I cannot do math. Now I have a graphon signal right now living on a one-dimensional torus. So therefore I can take a look at the Fourier sequence, okay? And I'm gonna assume my F to be band limited in the sense that the non-zero Fourier coefficient of F is only from -m to m-1, okay? And that is actually quite, I mean, this is a quite like harmless assumption, because if you take a look at the literature of Graphon neural network, there's a bunch of other band limited assumption, quite different from ours actually. But here's is when I'm gonna use a sampling theory in. So this work use Graphon theory and also sampling theory. So this is coming from Kluvanek. So I'm gonna write it down in case that you want to Google it. Sorry, sampling theorem. Let me just write it. Okay. Kluvanek sampling theorem. So it's saying that if you're living on the torus, and you know for sure that this F right over here is band limited, okay? And you observe that about like 2m is actually exactly 2m number of non-zero coefficient. Then you would be able to recover the whole F here. If you know the value, the sample value of F at the point 0, at the point 1 divided by 2m, at the point 1 divided F at the point of 2 divided by 2m, and all the way to 2m minus 1 divided by 2m. Okay, so 2m to come. If you're able to gather all of those sample points, you will be able to recover the whole F itself for the whole interval. Okay, but I'm gonna need something stronger than that. Let me just go back to that. I'm gonna need to sample way more than that. Okay, now that my support of F hat is in this like a band, I could assume it's actually in the integer interval from negative big N all the way to n-1, where n is much bigger than m. So I need to sample way more than the regular frequency. And in this case, I would have to sample at the point f0, f of 1 over 2n, all the way to 2n minus 1 divided by 2n. Okay. All right. So now we're going to go to the Graphon neural network construction. The idea is that if you're able to find me the sample values of the Graphon signal at this point, 0, 1 over 2n, all the way to 2n minus 1 divided by 2n, I will be able to construct for you a Graphon neural network that can generalize F from this known information. Okay. All right, so now I have only 2 layers. The first layer is just going to be input, which is the location of the abstract nodes, where it is on an interval from 0 to 1. And what I'm going to do is that I'm going to multiply that with the column vector 1, 1, 1, 1. That's going to give me a vector x, 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 right? And then I'm going to minus the vector 0, 1 over 2n, all the way to 2n minus 1 divided by 2n. So that's going to be taking care of this. Okay, so that's going to be a fine transformation. Then I'm going to do activation, which is just ReLU. Then I'm going to do the convolution against my future photo k. I'm going to represent it as tk. Whatever output here is going to be an output of the first layer, okay, which is going to be what a vector at every point x. And then at every point X, I'm gonna just take that vector and I'm gonna do a linear transformation, which is just gonna be a dot product with this row vector. And whatever output here is gonna be output of my Graphon neural network, okay? So now as I promised to you, I would have to show that the output is gonna be closely approximating my Graphon signal, okay? And the way that I'm gonna do that is that I have to show that this is approximately my f of x, okay? But I'm gonna go through a middle guy. The middle guy here is like r of r sigma, r sub r sigma, I don't know how to say it, sub r of sigma f. From here to here, I have integration by parts. From here to here, I have sampling theory, okay? Now let me just explain the sampling theory part a little bit. Okay, right over here. So this is gonna explain this part here. Okay. Now you could see that here I have my r of sub r sigma equal to a linear combination of a shifted function Sn multiply g r sigma. Okay, and shifted where? Right at the sample point j divided by 2n. The linear coefficient is exactly the sample values of f. Okay, Sn here is gonna be just some function. Okay, so just ignore the here's just a formulation for that. GN is a little bit funny, but let me just discuss about this approximation here. If I don't have this term right over here, I have exact equal sign. That is from the Kluvanek sampling theory, but I decided to put it in anyway. What is this GR sigma? GR sigma is basically a Gaussian on the torus. There is no notion of Gaussian of torus, so I have to make it up. Okay, so you could see right over here is basically the Gaussian on Z, right? This is basically a Gaussian on Z. You have a shape of the Gaussian, and then you restrict it to the integer, and then you bring it over to the torus. And I would have to truncate it as well. And I truncate it from negative r to r. That is because I view the negative 1/2 to 1/2 as same as the 0 to 1. They both one-dimensional torus. Okay. The reason why I have to do something like this is because I have to adapt to my support. The W has a support. W could be 0 somewhere. So I have to adapt to that. And that's why I have to put in a truncation. Okay. It's not going to be clear in this size yet, but let me just move to the next one. Okay. Okay, let me just tell you about the WNN theorem first, and then in the next slide, I'm going to explain more about why is that I need the truncation. Okay, so here is just a theorem. So you have a Graphon signal that is band limited, and I will be able to construct for you a WNN psi f that use only 2 layers. So remember that the filtering layer is only the first layer. In the second layer, when you apply the linear transformation, I use the linear weight that is from the supplied by the fsam row vector. Okay, and I will be able to have the such a WNN psi f that approximate f well up to epsilon error if I sample enough. So the number of like sample is going to be about 2n, and it has to be like epsilon to the negative 10 divided by 9. Okay. Let me just go back to the structure a bit. Okay. So, sorry. Oh, I find your question. Okay. Okay, so in the theorem, that's saying that I would be able to construct a WNN that has 2 layers. And what about a number of weights? The number of weights, so here you could see that I applied a linear transformation where I multiply x with the column that is 1, 1, 1, 1. Those are unital weights, so I'm not going to count it there. So I'm going to count a number of weights here. So it's going to be, the number of weights here is going to be just 2n, which is supplied by the fsam. Okay, so 2 layers, and I have like 2n linear weights that participate in my construction. But here's the thing, how does a number of weights compare with the error? You could see that right over here, the number of weight is basically just a rational powers in terms of epsilon. And there is a reason why, but there is a case where you could like have something that is much lower than that. Okay. Here I could explain why the alpha and beta to be like this. Well, alpha and beta appear in this formula for here. So R, the truncation level, is a power in terms of n, the power of n, and so is sigma. Okay, and I'm gonna choose alpha and beta so that this number right over here to be nearly 1. I could make this power here to be as close to 1 as possible, but then alpha and beta would have to be like very close to 1 too. I could push something very close to 1, but I could never get to 1. That's my problem. Okay. All right, let me just go to the main idea. Okay. Yeah, so actually, let me go back here. Okay. So as before, if I want to show that the output is approximately my Fs, well, I would have to go through this approximation first. And if you take a look at the formulation here, in order to show this approximation, I would have to show this approximately this right over here. Okay. And this is where integration by parts come in. Okay. All right, so that is the main idea here. I have to show this approximation. Well, if I take a look at this formulation right over here, this is just integrate against K. K looking like this when W is flat along the band, diagonal band. So suppose that you have W like just 1 along the diagonal band. You just have this. Now you could see integration by parts. Integration by part is going to give you the second derivative of ReLU is basically just a direct mass. Okay, but this one is exactly that. That is what I said. Okay, and now you could see why I decided to snug in a Gaussian, because the arrow term happened at the boundary. So if I have like Gaussian, it's going to be a small arrow that in terms of n, it's going to be exponential in terms of n over here. Okay, so that's what is approximation coming in. Well, what happened when you have a W that is not necessarily 1 along the band diagonal or constant along the band diagonal? Well, then it means that you would have to try to do integration by parts against a density that is Wxy over here. But you cannot do the integration by part against any kind of general density. So therefore, I would have to approximate my general density Wxy with a constant density. And that's where the whole error become rational power in terms of n come in. Okay. But you could avoid that case in the case when you have GN to be a sequence of unweighted graphs. When you have a sequence of unweighted graphs, then the W has a chance to be flat along the diagonal. But if you have like weighted graphs, then you would have to deal with a general density. So in that case, yeah, the error come out to be rational power in terms of n instead. Okay. Now, most of the work for this paper is coming in demonstrating the sampling theory on the regularized sampling theory on the torus, which is this one right over here. Yeah, which is this one right over here. Most of the work is coming on in this, and then the construction of WNN. And then you could see that the reason why we have the number of ways to be rational power in terms of error epsilon is not really because of the sampling theory problem, because you could see here the error here is exponential in terms of n. Okay, so if you have like W to be flat diagonally, what you have the error here is still e to the negative cn something. And then you convert that, that's going to be like n equal to log of 1 over epsilon something. So in that case, in the case where W is like completely flat along the diagonal, you do have the number of ways to be just log of 1 over error. Okay. In case it is not, then you would have to deal with a rational power. All right. All right. So once the hard work with the WNN and as well as the regularized sampling theory is over, it's actually extremely easy to construct a GNN structure. So let me just go back here. Okay. The only difference here is how to integrate this, because this is the only step that is not compatible with the general neural network, right? This is the integrating, continuous integrating against K, against the kernel filter K. But that is actually very simple. You just have to discretize it, okay? So in this case, you have, So in this case, you from the discretization, you're gonna have the graph filter looking like, let me just try to do this. So graph filter apply to a graph signal Fn, and let's just say xk is gonna be just summation of kn, xl, xk, summing over L, Fn, xl. That's all. So and this is coming from the discretization against this k, xy, f, y, dy. The 1 over n here is just because we discretize it using the Riemann sum approximation. And that's all it is. And you could see that from this kind of formula, the filtering, here's a spatial filtering, not the spectral filtering. Okay. And from that, everything is just nearly the same. You do have the two, the network, the GNN of 2 layers, the number of, okay, 1 filter layer, and the number of like linear weights in the second layer is the same. It's gonna be just rational power in terms of epsilon, provided that you have like W to be general density. But here's in order for the approximation to take effect, you do have to have like large graphs in order to have the good approximation. So this is only applicable for large graph where the number of nodes is at least like epsilon to the -4. Okay, and now the promise is going to be just the same. Okay, you might need you don't need to worry about this 5 here. So this is kind of measurement of like how good the output of the GNN psi and f is. The way that we measure it is that we map everything to the continuum. So this is an extension of the psi and f on the continuum from the interval from 0 to 1. Okay. All right. And for the random graph, for a random graph is also almost the same. Basically, everything is the same. You have 2 layers. The GNN structure you have is like only 2 layers, also the same number of weights. You have the GNN structure, it doesn't care what kind of graph that you're gonna give us, right? So if you put in a random matrix, well, then the output here, the Kn here is gonna act like a random variable. So right away that you know that you would have to use some kind of deviation inequality in order to get back to the case of like deterministic GNN. Okay, yeah, if you take the expectation of this is going to be giving you the adjacency matrix of the deterministic case. Okay, so then if you have the same GNN structure and you're giving it a random matrix, then the output is going to be as expected, like it's going to approximate your graph signal Fn well, but with the high probability. So that's all it is. Okay. And the way that we're going to do that for the case of like random neural network is, random graph neural network is we use this bounded different inequalities. Yeah, bounded difference inequality. So here, if you have like a function of like, oh, I didn't say it right. So if you have a function of like if some independent random variables, then the output of such function is going to be close to its expectation with high probability. So that's all that we get. That's all that we use in order to deduce a random theorem from deterministic theorem. Okay. All right. Let me just also go to the next slides here. So this is the reason why that I want to do this work on a Graphon neural network. So this is one of the theorem that I have in the previous work. So in this one, it's a little bit different. In this one, I have a manifold, and I have a function that lives on top of the manifold. And this function is band limited, and it is a different notion of band limit, by the way. Okay. And I want to be able to construct a GNN that learn my F well. And the thing is that in order to have a GNN, I would have to have a graph structure. And so I decided to use a lattice graph in order to approximate my manifold. And I use the same kind of idea. I kind of like embed the sampling principle in the GNN in order to learn my F well. Now the problem is, So I use the same thing. I use a continuous model and then I discretize a continuous model in order to have my GNN. But the discretization method that I have is only for one dimension. So what happened is that I have the huge chunk of my network trying to approximate a d-dimensional product. And the reason why I have to d-dimensional product because every point here is living on RD, right? I kind of have like approximation, discretize a continuous model in each dimension, and I try to multiply the discretization in d dimension. And that is the reason why I have up to log of 1 over epsilon to the d. And this is still a very competitive rate. But I remember I was really upset because huge chunk of my network just to use that to approximate a d-dimensional product. And so later I found out from my friend Jason, which is also a collaborator in this work, is that you could throw everything onto the continuum. And in that case, you don't have the problem of d-dimension anymore. Okay, so I think I'm gonna stop it here.
Questions also from people on Zoom? I have a few questions. So what you're proving is really like universal approximation properties, right?
Yeah.
But you said something about transferability in your title. Is this?
So the way that we think about it, because okay, yeah, you kind of catch it. You could say that I try to go fast. I think the screen frozen. Okay, you could say that in the statement of the GNN theorem, we kind of throw everything in the continuum. And the approximation is actually with respect to the limiting graphon signal instead of a graph signal. And it's kind of frozen. So I have, okay, let me just try to draw it. So psi, oh, here it is. So let's say in this case, you could see that, right? So I compare with the graphon signal instead of the graph signal. And that because I could use a 2 epsilon, right? I could use a 2 epsilon proof. So if this one right here is small, I don't know why what's going on. So if this one right here is small, and if n is large enough, and so is this guy, and plus 1 f small as well. Okay, so therefore, whatever output of the psi and f could be used in order to predict the either the fn, oops, sorry, either the fn plus 1 or the output of fn plus 1 f. Because the thing is, we do have like f. So, oh my God, I don't know what to do. So the Fn, the way that the graphon signal is the limit of the graph signal Fn is that Fn is close to F in L2. So the output here, F, could be used to approximate Fn plus 1. Or it also can be used to approximate the output of like side of n plus 1 f. So that's transferability. The output of like GNN in one layer, in a one level n could be used to approximate the future output of either fn plus 1 or side of like n plus 1 f.
We'll have to talk later. So that's not what I'm usually familiar with seeing as transferability. Anyways, but the other question I had was about the setup here. So is your statement that for any band limited f, I can find a graph? So the graph is part of the construction in the theorem?
Yes. And so it's sampled out of a graphon that is like we assume little about W as possible. So we could like sample the graphs out. But the reason why I have to do that because I try to avoid a lot of technicality. So let me just give you an example here. If I have the sequence of graph Kn, if I have a sequence of graph Kn, right? Let's just say here I have like 3, and here I have like 4, and so on. The limit is gonna be a W that is 1 on the unit square, 0 to 1 square, right? Okay. So this sequence right over here is certainly sample out of this constant graphon. Okay, it helped me a lot avoid a lot of technicality, because certainly I could have another sequence of graph. This is one of them, so this is like a kind of K3. I keep it the same. Let us say that for the K4, I decided to modify that, so I don't have this edge anymore. So this sequence, if I just modify it a little bit different, I still have the same sequence that go into the constant graphon 1. But then I would have to, like, you know, justify how to deal with this kind of graph K prime 4 here. So if I assume that my graphs already sample out the graphon, then I only need to do the Riemann approximation in order to approximate my W. But if I decide to have the sequence of graph that only matching to W, I might have to deal with this kind of situation where I'm lacking some edge or something. And that's gonna be an extra technicality. So I just want, for now, for the first paper, I just want my graph to be sampled out of the graphon. So yes, in this case, in the setup, I do want my graph to be the graph to sample out the graphon as part of the setup as well.
So in the theorem, there's a fixed graphon and there's a fixed F, or is it you're given F and you
so there's
construct the graph?
only a few things that is fixed. So the property, the regularity of W would have to be fixed, but other than that, it doesn't have to be anything else. For the graphon signal, the limiting graphon signal, the only thing I require that is just band limited.
And maybe I'll ask more offline.
Okay.
Are there other questions from the audience? Yeah.
So in the final result about the band limited functions, I think if you just use a feed-forward methods, you can already achieve dimension-free rate. So in your last estimate, you have a dimension dependence. Is that saying that GN is worse than feed-forward networks?
Can you say it louder, please?
So in your final result, you have a E log 1 over epsilon to
Okay.
E. But if you just use a feed-forward to approximate band limited functions, you won't have this
Right, in that work, the main thing that we try to show is that the GNN could, like the sampling principle could be embedded in the structure of GNN. And because approximation tool that we have is only allowed us to approximate 1 dimension. And that's how we have the problem with the log over 1 over epsilon. So the main idea for that work is just we really try to put the sampling principle into a GNN. That's what it is. We didn't think about that approach. Yes?
In terms of sampling, are you referring to sampling the neighborhood of GN when we view GN as in operations? Like in GN, there is explosion in the neighborhood, right? And there are sampling based on whether we should keep this neighbor or we should move to the next to keep the most important neighbors to reduce the computational cost.
I actually didn't think about that way. Okay, can you repeat it again?
Okay, so like in GN operation, like the convolution actually introduced a lot of,
Okay.
yeah.
Yeah, so yeah, I mean, this is also a technicality that I kind of avoid. Okay. 2 things. If you talk about my past work, you could see that the way that I sample is I sample outside the prediction zone a little bit. So you could see this is like the prediction zone is right over there, and I sample outside. That because of home convolution thing, you have to like have more neighbor around the point of the prediction zone. Another thing here, which is also something that I try to like put under the work as well. So you could see the prediction zone here is from R to 1 minus R for this problem right over here, because again, convolution problem. But this prediction zone is gonna go to, it's gonna stretch to 0, 1 when n goes to infinity, because R is like, reciprocal of n. Yeah, so it's a statement here is that you predict a smaller portion of network instead of the whole network itself.
So it's like in some sense we're easing the oversmooth problem in GNN as well, using Graphon neural networks.
I don't understand what it means. For me, the main thing for me to use Graphon is just I want to put in a sampling principle where I don't have to deal with the d-dimensional problem.
Okay.
You say it's gonna be easing. Can you repeat it again?
Okay, so in graph neural networks, because like the convolution again, we're actually using the neighborhood, the information extensively. So when we stacking the layers, actually all the nodes will have similar representations. So like here, because you're kind of using some different sampling strategy, would that also help the oversmoothing problem as well?
The way that I understand the oversmoothing problem is when if you decided to apply way too many filters.
Yes, that's when it's.
Right. I mean, in this case, we only have like filtering once.
Yes.
So yeah, I mean, it's certainly because it's like there's mathematical principle embedded into the structure,
Right.
so that you could have like good approximation. Yeah, and the way that we do that, if we use the integration by part trick, you could say that like second derivative value is just like direct delta. And that is the way, the principal way for us to embed the sampling principle in. You would have to use the value activation. Yeah, I mean, even in the previous work, the filter that we only use once, because again, we use integration by part, kick it up on the value, and then you have the direct delta. So we don't really need to use a lot of filtering. So we don't really have like over smoothing problem.
Okay, thank you.
Okay, since we're a bit over time, maybe we'll save other questions for after the talk.